Hi, my name is Matt Holliday and welcome back to my Go class. So I want to do something a little different now. I want to talk about pointer and value semantics and how they work in Go. And what that gets into is the question of like, when do you use pointers and when do you use values and what's the trade-off and what are some of the gotchas that can happen. We've seen closure capture and I want to show a few other things like that where we may have a problem taking a reference to something if we don't think about what we're doing. Okay, so I want to start with a fundamental idea about pointers and values. And probably mostly in the context of structures, but that's not here or there. And that is that when we use a pointer to something, in many cases what we mean by that is we want to share it. We don't want to copy it, we want to share it so that different functions or parts of the program are modifying the same data. Conversely, if we're copying it, it's because we don't want to share it. Okay. Now, in a lot of cases, not sharing things is safer, and that's going to be particularly true when we talk about concurrency, right? The best approach to concurrency is don't share anything. So why do people choose to use pointers? And here are a few of the examples, and I'll illustrate a few of these. So first off, we may have something that can't be copied, and I'll show an example or two of that. So if we can't copy it, we must share it, and we must therefore use reference semantics. We have to take a pointer to it. Okay. Another example is going to be efficiency. Once an object gets large enough, it's more expensive to copy it than it is to use a pointer to get to it. And there's a cost to pointers, right? The short version is, if I use a pointer to get to something, well, first I have to read the pointer variable out of memory, and then I have to do a second memory read to get the actual data. So that's 2 trips to memory instead of 1, and the cost adds up. Okay, surprisingly, the cost adds up. Now, there's a third reason I don't want to really get into, I'll just mention it, and that is once we start talking about object-oriented programming and methods, we may want to have a method that changes the object it's called on, and that's going to have to be reference semantics. Obviously, if the method is called with value semantics, we get a copy of the object, we calculate something, but we can't change the object permanently from a method that uses a value semantic. We've already seen the next case where we want to, for example, decode protocol data, right? So when we did our JSON unmarshal, we had to pass a reference so that the JSON code would have a place to copy the data back into when it decodes the JSON. And our final case is the case where we actually want to have pointers so we can have the concept of null, okay? You know, it shows up in databases, but it's not just there. If I build a tree structure, and we've done that a couple times already, typically we have pointers to nodes, and we want the whole concept of being able to have a nil pointer to say, hey, this node doesn't have children. So here's an example of we must not copy something. And again, I'm jumping ahead. We haven't talked about what a mutex is yet because we haven't done concurrency. But for the moment, let me just tell you that a mutex is a thing you can't copy. If you copy it, it stops working. And so any structure that has a mutex in it, we're going to have to operate it using pointer semantics or reference semantics. We have a function do, and it has to take a pointer to the employee record and lock the mutex. If it got a copy, then the lock is meaningless. Now, this is not a terribly exciting case because the only reason we would embed a mutex into a structure is because we're going to share it in the first place, and therefore we'd use reference semantics in order to share it. There's another example, again, it's getting forward into something we haven't talked about. There's a structure also used in concurrency. Pardon my bad handwriting. It's called a weight group, okay? And often we have a function where we pass the weight group as a parameter. We're always going to have to pass it as a pointer because a weight group is another concurrency structure that doesn't work if you copy it, okay? So the only way we can ever pass it as a parameter to a function is by taking its address, okay? Now, there's another side to this of, well, we may or may not copy. It's perfectly okay to write a function that copies a struct in, changes it, and passes it back, as long as we actually pass it back. So here I have my little widget type, and it's very small, it's 2 integers. So I could take the widget in, modify it, and then return it. Now, if I don't return it, the modification will never be visible. But this is a choice, this is an alternative to taking a pointer to a widget, is to take the value of the widget, change it, and give it back. And this is kind of the thing you see in functional programming. right? In certain cases, it might be a little safer. Now, is it efficient? And the answer is, if your struct type or whatever is less than 64 bytes, this is probably perfectly okay. All right, and you'll see Go passes around things like slice descriptors and string descriptors that are 16 or 24 bytes. They do that all the time. Okay, we don't pass around a map or a string descriptor by its address. We do pass around the actual underlying data because the descriptor is referencing underlying data. But the actual descriptor just gets copied. Again, 16 or 24 bytes, big deal. Now, I've worked on a system where we had a data structure that represented a 4K block of data, all right? And if you start copying 4K blocks of data, your program is going to slow down really badly. And so you're not going to want to do that. You're going to want to use a pointer to that thing that's 4K, and you're going to want to deal with it through the pointer. Whether you meant to share it or not doesn't really matter. The cost of copying the 4K block of data from one place in memory to another is just going to take a huge whack on the performance of your program. So that's a case where you're going to use discretion and use reference semantics for efficiency. Now, when I talk about reference semantics, I also want to make a little pitch about consistency. Okay? If we're going to use reference semantics, we should probably use them consistently. And this is an example based on something Bill Kennedy said in one of his classes. And the example here is, I've got some process. I'm going to do employee relocation in my software that manages the employees in the company. And to do that, I'm going to call a bunch of functions. So I start out with my employee record, and I'm going to pass it around through a pointer. Fine. I had a reason for doing that, which is great so long as all the functions take pointers. And the problem here is, well, somebody said, hey, for function 3, I'm going to just take a copy. And doing that causes a problem, because let's suppose I pass that to function 4. Function 4 makes a change. It changes my employee record, okay? But that change will never be seen above function 3 because function 3 made a copy. So in the middle of this call chain, I made a copy of the data, and below that, I'm mutating the copy, and any change made really in F3 or below is no longer visible to the actual original employee record that was passed into the top. So if we're going to go down the road of using reference semantics, particularly if we're doing it for efficiency, we need to make sure we're consistent in our function signatures, that they're all on board using reference semantics. Okay, so I want to talk a couple things about allocation. I'm going to do a lot more about performance in mechanical sympathy, but right now I just want to mention, generally speaking, stack allocation is more efficient, and Go will try to allocate things on the stack. And when it does that, generally speaking, it's going to be able to not use pointers, and again, that's more efficient. So it's more efficient to put it on the stack for a lot of reasons. Garbage collection reasons, the way the cache works on the machine, and the fact that we don't necessarily have to have a pointer to get to the data. All right? It's generally also better to have dense data. All right? It's better to have a bunch of data in a slice than a bunch of data spread around in memory. So, and if you go back to older languages, they always typically allocated on the stack unless you used a special function like new. All right? And then you get to interpreted languages, which almost always put things on the heap at great expense. So we've already seen in the scope versus lifetime stuff that sometimes things have to go on the heap. All right? And Go is doing something called escape analysis. I may have mentioned this before, to try to figure out which things have to be on the heap instead of the stack. It wants to put things on the stack, but it can't always. Okay? So obviously, the case where you return a local variable through a pointer, or the case where a closure closes over a local variable, and there's some others. Okay, there's some cases of things that it just can't do escape analysis on because they're too complicated. Now, why do I mention this? Okay, there is a new function in Go. I'm not really going to talk about it. If I have some type X, then, creating a new X is the same as creating an ampersand X with an empty initializer, and the second format is usually preferred. And so, new is not that common. And one of the other reasons for not using new is it's going to confuse people who come from some other language where they think new means it's going to go on the heap. And in Go, new has no part of that decision about whether it goes on the heap or not. You can create something with new, it's on the stack. Something else you create with new might end up on the heap. And that's a good reason to avoid new because it avoids that confusion. Okay, so now I want to get into some special cases of things where we want to think about reference and value semantics. Several of these are going to have to do with for loops because, you know, that's where the exciting problem comes from, right? So, as I pointed out before, when you use the range operator in a for loop, the value you get is a copy. So thing, in this top case, is a copy of an element of a slice or an array, right? If it's really big, you probably don't want to copy it. That's an issue. But if you want to mutate it, that's also an issue. So if I want to take, let's suppose thing is some structure and it has a field and I want to change the field. Well, if I change it in the copy, that change will no longer be visible outside of this loop iteration. So it's much more useful then to do the one variable range, get the index, use the index to subscript into the original slice or array, and change it. This change down here will be visible after the loop is done. And if I didn't do it that way, if I tried to actually up here, if I did, you know, thing dot which is equal to some value, well, that's good until I hit this little closing curly brace, and then it just disappears. All right. The next thing I want to mention, and I've probably said this several times, I've talked about when you use append, right, you need to assign the result of append back to the original slice variable, because append could cause the slice to get reallocated if it grows beyond a certain limit. Well, this is also going to be true if you call a function. If I have a function that takes a slice, and I want that function to be able to modify the slice, maybe it's going to put some more stuff in it, then I have to return the slice. And you'll see functions like this. So I take the slice in, I change it, I have to return it. Because if I don't return it, and the slice here called things gets reallocated, then that reallocation disappears as soon as the function is over. And therefore, all the stuff you just appended to it, that append is a no-op. It disappears as soon as the function is done. Okay? So if we take a slice and we want to modify the slice in a way that the rest of the program should see it, then the safest thing to do is to return the slice as a return value. Okay? You could take a pointer to the slice. That's less intuitive, and I think the style here I'm showing on this slide is better. So there's another gotcha with slices. I talked about, in the last segment, I talked about maps. And if you look up something in a map with a key, you can't take the address of that thing that's inside the map. And the reason for that is, well, maps rearrange themselves internally all the time. Now, Go will allow you to take the address of an element in a slice. But slices can also reallocate, right? So it's maybe not quite as dangerous as a map, but it's still dangerous. And the example I've got here is a perfectly good example. If I run this, right? So I've got some user struct, and I've got a little function that takes a user and changes the count. Okay, and then I created a couple of users, right? And then I did a risky operation. I basically made a variable Alice, and Alice is a pointer to the first entry in my slice, okay, which represents Alice. Fine, that's good as it goes. The only problem is that right now, in almost every case when I run this, users is going to be a slice with length 2 and capacity 2. It doesn't have any extra capacity. So I add Amy to my list of users, and the slice reallocates, okay, right here. When I do this operation, users changes in the sense that the underlying array with the users now has 3 users and it's in a different place. And so when I now call add to Alice, and add to Alice takes a pointer to this Alice that I saved, well, okay, so there's 2 things to say here. The first is it's safe in the sense that my program won't crash because garbage collection, right? But what is my Alice pointer? My Alice pointer is a pointer to the original slice before I added Amy. And now when I go and print the slice afterwards, so I do my add to Alice function through a pointer to a slice element, but it's in the obsolete version of the slice. And now I go print my slice afterwards, okay, and Alice's count didn't change in the copy the rest of the program is using, right? I ended up with a pointer to an obsolete or out-of-date slice because I kept a pointer to a slice element. So I really don't recommend doing that. I mean, it might be okay if you're doing it in a teeny weeny little bit of code where, you know, nothing else can happen, but it's just not a good idea. For this next piece, I'm going to work in the playground so I can animate this, because I'm going to need to change the code as we go. I've got a little bit of code here which has a slice of 2-element arrays. Okay, that's what this type is up here. So items is a slice. The type of the slice is an array of 2 bytes. I could have made it int, doesn't really matter. And it just has values, right? So the first entry in the slice is the array with the values 1 and 2, the second entry in the slice with 3 and 4, and so on. And I have this desire to make this into a slice of byte, which means I'm actually going to create a slice from each of the array entries in items and put that into A. And if you haven't seen this, this is the slice operator with no values, and so it just means take the entire thing, right? If I just have a colon, that means go from 0 to length minus 1 and, you know, slice the whole array. So the whole array of this item is being appended, right, as a slice. When I run this, I'm going to get possibly surprising output. Although if you've been watching some of my other videos, you may already have an inkling this is not going to work. Right? And it doesn't. I print out the original items and I have my little things in there, 1, 2, 3, 4, 5, 6. And then I print out A and it's all 5s and 6s. Okay? I should have done this so it's all 6s and 7s. I'm sorry, I just didn't think of that. Okay? So what's going on here? Well, remember, item is a copy of an entry in the items slice. So item is a 2-byte array. It's a copy of a 2-byte array at a particular location in memory. And every time I go through the loop, that copy is in the same place. So the copy of 1, 2, and the copy of 3, 4, and the copy of 5, 6 are in the same location. And my slice gets a reference to that location. So my slice here, right, is not picking up the values. It's picking up a pointer to where the values are stored. And when my for loop is done, okay, what does item end up having in it? Well, it has the last thing it had going through the for loop. And the last thing in the for loop was the last 2-byte array with the values 5 and 6. And so all 3 of these slices that are inside the big A slice, because it's a slice of slices, all 3 of those slices point to the same array with the same values 5 and 6. Okay? Now, we saw this in the context of closures, and we said something about closure capture. But there's no closure here. It doesn't matter. Okay? Again, we're keeping a reference to the variable that's given to us by the range operator, and we're using it later after the loop ends. So if we were using it inside the loop, if we were using it only inside the loop iteration, we'd be fine. But we're keeping those references to the loop iteration variable, item, and using them afterwards when the loop is done, and they all refer to the final value of item. And unfortunately, there's only one way to fix this, and it's to make a copy. We saw that before, where we had the little closure capture comment next to a copy. We made a local variable inside the loop, and we're going to do that. Except for a slice, it's going to be a little bit more involved, right? So I'm going to make a byte slice, okay? And I want to make it with the correct length. So right now, I already know how big it needs to be. Whatever the size of item is, that's the size my byte slice needs to be. So I'm going to go ahead and create it. So each time through here, I'm going to make a new slice, which means it has this new invisible backing array, and I'm going to copy all the values from items. So what am I going to append? Well, I'm going to append I. And now, each time through the loop, I is a unique. And so instead of saying closure capture, I'm going to say make unique. I is a unique slice for that iteration. And when I run this, I get the results I expected. Now, I'm not showing types. The first is a slice of arrays, and the second is a slice of slices. But in terms of the data, if you think of just the data itself, it's the same now. Okay? So we've overcome the reference problem by making our own slice inside here. It's just we had to do it in 2 steps. We had to make a slice of the right size and then copy. So now the only question I've got, and I haven't actually tried this, is what happens if I make it with capacity but no length? And it didn't work. Okay, so I kind of had the suspicion it wouldn't, because copy says, hey, I'm going to use the length of one or the other, whichever one's less. And if I make this with capacity but no length, then the copy says, well, there's no length to copy into, and so I won't copy. All right, so we actually have to make it this way. We make it with a byte slice and a length. It gets created with a bunch of 0 values, so we do a little bit of throwaway work. But that way the internal copy function can just do it. Copy will take the 2-byte array and copy it into the 2-byte slice. So not to beat a dead horse, but I've got one more example of this that's, similar but different. And that is on this slide, I've got a little bit of code that's part of a GraphQL engine. I've got some server, and the server is producing GraphQL, and it's doing it, this is handwritten code. So I've written a GraphQL resolver, and my resolver is going to generate some data that will be used to generate the JSON that the server sends back. Right? And it's going to take some offer and produce a list of changes. So it's going to return the resolvers, a list of resolvers for the next lower part of this tree. Okay? And, that's as far as I want to explain how GraphQL works. So I've got my result, and I'm going to return my result. And I've got another loop. I'm going to loop over some slice or array of changes, right? And so I've got my local loop variable change, which is a copy of one change. And unfortunately, the way this works is I'm going to put a pointer into this structure. For whatever reason, I'm returning a slice, and my slice has change resolvers with pointers. And guess what? I've just done the same thing again, right? I am keeping a reference to this one variable change. And so I actually saw this, this created a bug, because we returned a list of changes where the only change you saw was n copies of the last change, the one that was last seen in the loop. All right? And again, we fix this by doing a local variable, right? So, but instead it's not a closure capture this time, again, because there's no closure here. But I am keeping a reference to something I'm iterating over, and I can't do that by taking the address of the loop variable. So again, inside my loop, I make a local copy, and then I take the address of the local copy. And so now when I'm done, this slice of change resolvers, every one of them has a pointer to a separate change. Okay, so I just went through some ideas about pointer and value semantics, or reference and value semantics, in a couple different dimensions, sort of like why would you want to use them, and then also some questions about issues. And of course, the single biggest issue in Go is anytime you take a reference to a mutating loop variable and you keep it. So we've seen that with closures. Now we've seen it with copying it into some data structure like a slice. And of course, we will eventually see it with Go routines, because that's another place it shows up very commonly, but we won't see that just yet.